Welcome to video number 5 in this series of tutorial videos for HDXmodeller. And in this video we're going to go over the output files. So these are the files that are emailed to users once the optimization is complete, and also two different input options. So once an optimization has finished, a zip folder is emailed to the user, and this folder contains several different output files as seen here. I think there's 15 altogether. So I just want to go over these relatively quickly here. So the first two files here are optional files for constrained optimization, and we'll go over those in a short while. The second two files here are the residue specific validation in the form of the delta R matrix, and I think I went over that in video 2. One of these is an image, so PNG, and you also have the text file of the values. We also have some other residue specific validation information in the form of histograms, which are a plot of the density of the optimized protection factors over the whole optimization. And again, information about these can be found in video 2, and information on these and also the delta R matrix can be found in our communications biology paper. We then have this file here, this image, which is actually one of the main outputs. This is a summary of the results. This contains an image of the input data, and also the macroscopic, so the peptide models and the optimized protection factors. I think this was mentioned in video number 1. There are some other validation outputs. These are for the peptide errors. We have an image here and also the data. More information can be found about these in our analytical chemistry paper on noise handling. For housekeeping, we also email back the input files. So this is easier to keep a log of what input data actually generated these outputs. So obviously we have the experimental RFU input, and also the chemical exchange rate file, which was probably generated by a KINT tool. The main outputs, or one of the main outputs, is the optimized protection factors. Of course, we have two outputs for this. The first one is taken as the median over all replicates, and this should be the one that is referred to as your main output. These values are also found on this fig opt PNG. We've done some testing in terms of the best central tendency to take over all of the replicates. The median tends to perform the best, but we also have a secondary file here which contains all of the optimized protection factors for each of the replicate optimizations. Then I have a log file with information on the optimization. We have the RFU models over all optimizations, over all optimization replicates. This information can also be found in FigOp. And finally, we have the main validation output. This is subsection specific validation in the form of the covariance matrix and the R matrix score. I just also wanted to go over two different input options in this video. One that I haven't covered so far, which is this option here for constrained optimization. And I also want to give a little bit of information about the different loss functions which are available on HDXmodeller. So after every optimization, as you've seen in a couple of slides ago, the folder that's emailed to you will also contain 2 files which can then be used to constrain optimization in any subsequent optimization. So there are 2 files. This is the one that is required to be uploaded, the one beginning with const gen and then the name of your optimization. And if this file, this text file, is uploaded, then it will apply a constraint of plus or minus LNP, which is the natural log of the protection factor, to specific amino acids for any subsequent optimization. And you can't specify the tolerance of the constraint, nor is it possible to specify which amino acids will be constrained. We've done some testing, and this is based on our own experiments. So applying constraints to an optimization typically does have a really large effect on the optimization outcome. This can be seen here, where we have our reference LNP against the modeled or the optimized LNP, and applying a constraint to these data affects this change from red to blue. So we see this really large increase in the accuracy of the optimization. The problem with applying constraints, what we found, is that it's very difficult to predict whether applying a constraint will worsen or benefit your optimization. Fortunately, the R matrix parameter is highly capable at differentiating whether a constraint has improved or worsened your optimization. So we can see this in this image here. For these data, as we go from red to blue, we have this increase in accuracy, and this is also reported in the R matrix term, which is given here in the top. So if you want to apply constraints to your data, then we recommend you follow this protocol. So constraints should only be used following a production run. So that's an optimization that has had at least 50 replicates. Once this has been done, then you can apply the constraint file and then re-optimize the data for another 50 replicates. And then you should use the constrained outputs only if the R matrix from the constrained optimization is at least 0.05 higher than the R matrix of the optimization that wasn't constrained. So finally, in this video, I want to talk a little bit about the different objective functions. HDXmodeller has 3 different options, which we term forced, relaxed and hybrid, as shown here. Now, the loss functions can have a really large effect on the optimization. I don't want to go into this into too much detail, but what these plots show here are the loss functions and also the gradient for the optimization with respect to k-obs. And so this k-obs value here is actually what is updated iteratively during the optimization, and this can have a large effect on how the optimization performs. In general, the way these objective functions work is that they affect a change in the way that the error surface is explored during the optimization, and of course then that can affect the outcomes. So the problem is that objectively there's no good or loss, no good or bad loss function. Different ones can perform differently in different situations. What we have seen experimentally is that different loss functions can affect changes in the optimization outcomes. So we see this in this image here. Unfortunately, a little bit has been cut off, where we're looking at this figure here reports the change in the accuracy as we go from the forced to the relaxed objective function for 30 different reference data sets. These are the data sets that we used in our initial paper, and you can see that when we change the objective function, we have this difference in the accuracy. of the outcomes. So the useful thing here is that, again, the R matrix parameter can differentiate whether the use of a different loss function has caused a change in the optimization outcomes, and whether that change is better or worse. And so really this is part of our sort of so-called sandbox approach, where it might be useful in some instances to try and re-optimize data with a different loss function, and then you can use the R matrix parameter to decide whether that's actually benefited the outcome. The relaxed objective function is chosen by default, and the reason why this is chosen by default is that in general it tends to perform better than the forced objective function, and it has improved noise handling capabilities. The hybrid approach has the best noise handling capabilities. So that's the end of that video, number 5. Thanks for watching, and I'll see you in video 6, which will be our last video.